Okay, so now we are recording and we're going to the slides on support vector machines. And again, I can't see my tabs. Is this my tab? I don't know. Is it? Oh, yes. Okay, so this is mostly what I did during spring break is make these slides. So here's just two data blobs that we're going to use to sort of, show how the support vector machine works. So one way of understanding what a support vector machine is it's just a kind of linear classification, except it has sort of regularization built in. You've tried to find a separating line. Somebody probably needs to mute. Do you guys mind muting? I can hear like cars. It sounds like I'm listening to Fast and the Furious or something. It's probably not even fast cars driving by, but maybe it is. So we try to find the separating hyperplane with the largest margin. So here's an example of a line that separates these two data blobs, but the margin, which is the space between these two dark black lines, that's small, and here it's big. So how do you make the margin? You just push out from the separator until you hit a data point on one side and a data point on the other side. Those data points that get hit are the support vectors. So that's why it's called a support vector machine. This idea was invented in the 90s by, among other people, Vladimir Vapnik, who is like a machine learning master, legendary kind of guy. So since this is linear classification, the decision boundary is still just given by a hyperplane, and so the hypothesis class is exactly the same. So this dashed line here is just the dot product of w and x. You set that equal to 0, and then the x's that make that equation true are what determine the dashed line there. So it's the same hypothesis set that we've been working with forever. So just because of the mathematics behind the way support vector machines work, it's usually presented in a slightly different way, just different notation than we normally use. So we normally have these sort of dummy well, here it's a dummy variable, right? This is the bias bit. It's always 1, and we do that so that the bias coefficient here can just be a part of W. So in the usual presentation of support vector machines, this is what's called B here, and then you don't have this x0. You have just x with only sort of the functional features there. So then if you take the dot product of these two, and then you add the bias weight at the end, it says exactly the same thing as the equation that we normally use. It's just that for the mathematics of support vector machines, sometimes it's convenient to be able to sort of talk about that B in isolation. So what I'm going to do is I'm going to keep our traditional notation, and I'm just going to use sort of Python array slicing to remind everybody that we're throwing out the 0th coefficient here for the x and the w. So when you see these little parentheses down here, that just means we're doing a little array slice that ignores the 0th element. Okay, I hope that's clear. So clear all this. Okay, can we go down? I have to stop this before I can go down. Okay. So the decision boundary is what it usually is. It's just the 0 set of the dot product of the weights and the feature vector. And here's what the margin lines are. So it's kind of funny that they're always so simple. The upper margin is just it's the x's that are the solution to the equation w dot x equals 1, and the lower margin is just the set of solutions to the dot product equals -1. But I think the explanation for why that's true is best seen by looking at what's happening in 3 dimensions. And let me see if I can get my pen back here. Come on. Okay. All right. So this is a plane. You know, that's the plane like z equals wx, where this is like the z coordinate here. And so here, this x does have a bias, but these points are just in the xy plane down here. So when I plot these points, I'm ignoring the bias coordinate, and this is so x is just 2-dimensional data. You know, so this defines a plane, and then the zero set of this is what defines the separating boundary here. So if I set this equal to 0, then there's a certain set of solutions to that equation in the feature coordinates. And so when I graph it, it looks like a boundary. And so that's this line here is just the 0 set. So what happens if you set the dot product here equal to 1, let's say. So here's 1 on the z-axis. And so if you set the z coordinate at 1, and then you look at the restriction to this plane here, you get another line. And then if you project it down to the xy plane, that's what makes this margin line here. And the same thing happens at -1. So if you look at what happens on this plane at z equals -1, you get a line in space there, and then you can kind of project it onto the xy plane, and that's what gives you this lower margin here. So obviously there's something special about W if the solution to this equation just happens to go through these support vectors here. And there is, and it's just part of the optimization process that picks W. So W is picked so that happens. Okay, so let me clear these and go down a little bit. To close this. All right. All right. So actually, let's go back to this picture a little bit. So those of you who've had multivariate calculus, you might know that this plane here is a surface that's a function of 2 variables, which we are like whatever these 2 coordinates are called. We could call this the x1 coordinate, and this could be the x2 coordinate here. So if you take the gradient with respect to x1 and x2 of the expression w dot x bar, then what is this going to be? So this is the gradient of b, the bias, plus w1 x1 plus w2 x2. So we're taking the gradient with respect to the x variables here. So this is going to end up just being w1 when we take the derivative with respect to x1. Then w1 will be the sole survivor. And w2, when we take the derivative with respect to x2, then w2 will be the sole survivor. So that is what we call w, and then with the array slice. Okay, so that's our weight vector ignoring the bias coordinate. So what does that tell you? That tells you the direction, the uphill direction for this plane. So that means W is going to be pointing in this direction. So this W is going to be pointing in the direction that is uphill for this plane. And what's more, so the magnitude of the gradient is going to be So if I take the magnitude, this is WT x here, and I look at its magnitude, then the magnitude of this arrow is the steepness of the plane. So if the magnitude is small, that means that it's not very steep, and if the magnitude is large, that means that it's a really steep plane here. It's going to cut through the same decision boundary either way. But notice there's a free variable here as far as like the slope of the plane that does the cutting. You could have a really steep plane, slice this, or you could have a really shallow plane, slice that. Okay. So let's go back down here. So the steepness is controlled by the magnitude of the weight vector. So the smaller the weight vector is, the more gradual the slope and the wider the margin. And so why is that true? Let's just look at this here. So if this plane is making a shallow cut here, then it's, by the time you get to 1, you're going to be further out. So it's going to make a wider margin. On the other hand, if this plane is going through the decision boundary at a really steep angle, then you're going to get to 1 quickly, and that's going to make the margins narrow. Right. Okay. So that kind of, we mentioned that because this is part of the criteria for picking the W that the support vector machine picks. So let's look at the simplest case first, and that is just the case in which the data is linearly separable. So this is called hard margin classification. So let's just try to phrase what we want W to be in terms of optimization problem. So maximizing the margin width means minimizing the magnitude of W. The problem with this expression, let me see. Come on, give me my pen. Give me my pen. Come on. Sorry, this little thing has to drop down. Okay, there it goes. Man, I've got to figure out a way to do that faster. Oh no, and then I just made that ugly streak. Oh gosh, something's wrong. Turn it off. And now I've got to fix that. Clear all drawings. Clear my drawings. I think it's Zoom is not behaving well here. So we want to minimize this. If you think about what this looks like, let's just say that the W is two-dimensional. So you have these 2 dimensions, W1 and W2, and then if you were to make a plot, a 3D plot of the magnitude, it would be kind of a cone. It would be a cone, and if you plotted it in 3 dimensions. And the problem is that the derivative here is not very nice. You know, it's not differentiable at the origin, and it sort of always tells you that the slope is the same even when it's really close to the minimum. So it would be better to work with something that had the same minimum, but it was just a little bit more gradual, a little bit more like a paraboloid. And that's why we use this formula instead. So this is sort of softer like this. So now it is differentiable at 0, and also the closer you get to the bottom, the smaller the gradient is. So it's just kind of a nicer surface to work with. Okay, so we are going to, here's what we're going to minimize. We're going to minimize that. And so that's the objective function. And what are the constraints going to be? We want all of the positive features to be sort of on one side of the top margin. So this is the margin for the positive examples. And then there's going to be a lower margin for the negative examples. So this is just saying that we want all of the training data to be outside of the margins, with the positive examples on one side and the negative examples on another side. So something kind of cool here is that this -1, you can just think of that as this -1, and this +1 is kind of like this +1. So instead of having something defined by cases here, you can just have one expression by multiplying in the y. So this is kind of a cool way to encode it all. So look what we have here. We have one objective. This is just the thing that we want to minimize. And how many constraints do we have? We have a set of n constraints. So this was a hard part for me when I was learning about support vector machines, is I just couldn't believe that there were that many constraints, I guess. But we have one constraint for every training data point. Okay. So how do we solve that optimization problem? We're going to punt a little bit, except that we'll say we're going to use what's called a quadratic programming solver, but we'll at least explain what a quadratic programming problem is. So this isn't discussed. Oh yeah, where can you actually read about support vector machines if you don't like my notes? So my notes are more or less just based on this book. This book has an excellent 12-page presentation on support vector machines. So our textbook has a supplementary chapter on support vector machines, which is probably better, but it's 55 pages long and it's pretty hard. So I suggest you read the hands-on machine learning book first, and then if you have time or you think you might like to go to graduate school or devote your life to this stuff or whatever, then read the Abu Mustafa notes. So what is a quadratic programming problem? It's when you have a quadratic objective function, which we do, and I guess I'll say more about that in a second. But you guys know that this is just a sum of squares, right? So it's a quadratic, NW. And you have a linear system of constraints, and that's why this looks kind of jagged here. So this is just a system of linear inequalities, and so it looks kind of angular. And what we do in a quadratic programming problem is we find this point inside the constraints that is closest to the quadratic optimum. So, all right, so that's it. So we've got some kind of quadratic function here, and we're just getting as close as we can to the optimum while respecting the linear constraints. That's a quadratic programming problem. And there are several solvers for quadratic programming problems in Python. I think I get the impression that this one is the best one, and probably the one that I picked is the worst one, but I thought it had the simplest interface. So I picked it because it was simple, not because it was good. So, you know, why do they call it programming instead of just quadratic optimization or something? It's because when you have these problems, you have to find some way to express it in these kind of awkward terms. So when you use a QP solver, you have to find some way to express your optimization problem in terms of this language here. So this first line here is just a general quadratic function in W. You know, if you have like WT GW, this is like the sum over I and over J of Wi, G, Ij, Wj. So that is like it's quadratic in W because it's adding up a bunch of terms that have, you know, a product of at most two elements from W. So that's what it means to be quadratic in W. It's like a square. So this will include, you know, W1 squared, W1 times W3, etc. And then you have this, and this is sort of like the linear term. You know, this will be like AI times WI. So you have this sort of like degree 2 part and then this degree 1 part. So that's just a general quadratic function in a multivariable setting. Then you have this thing, which is the constraints. And so somehow this is going to be expressing our set of constraints, yi wt xi is greater than or equal to 1. So we have to somehow express this. Remember, we have a whole bunch of these. So that kind of connects with a matrix, right? Because a matrix has rows. And this inequality is actually kind of is coordinate wise. So maybe so do I just have an eraser here? So here we actually on the left, we have a whole vector of things that we want to be true. And I hope this is the pencil. And on the right, we have a whole bunch of, right? So we want this to be true, but we want that to be true sort of in every coordinate. So V will be this vector here, and AW, when we figure out what A is, will be this vector of, so we just want the stuff over here in this vector to be bigger than the stuff over here in that vector in every single coordinate. And this sort of explains what the variables mean in terms of our notation, because we use D to stand for the number of features. And here, in this case, K will just be equal to N. But later, when we do other kinds of, so N is the number of data points. And more complicated quadratic programming problems that we're going to be talking about in just a second, K can be other things. So this is the programming part, is finding some way to sort of ask the QP oracle your question. All right. And, oops. Okay. So here's the connection between the generic quadratic programming and the way we describe the hard margin support vector machine. So the thing that we want to optimize is, let me get my pen again. Okay, so the thing that we want to optimize is this. So you can write it as this. And so, we've looked at things like this a couple of times before. This is pretty close to just being the transpose of W times, I. I is the identity matrix that doesn't change anything. So this would be equal to 1/2 WT W. The only problem with that is we don't want to do it for the full W vector. We want to ignore the 0th element. So instead, we just do it with this matrix. We've called it A before. I guess I should call it G. So G is just like I, except the first coordinate is going to be 0. So G is going to look something like 0, but then otherwise it's going to look just like I. So it has a bunch of 1s on the diagonal, and then it has a bunch of 0s over here. And this first coordinate, which is like G00 is 0. And then it has 1s on the diagonal. So when you do that, then you get exactly what you want. Then WTG, W is going to be equal to, there's a factor of 1/2 here, is going to be 1/2 of WT, and then the slice, W, and then the slice. Okay. All right, so we've sort of just solved that problem. Except writing down what to do and then typing in the code are not exactly the same, I know. But anyway, we've solved the problem of determining G, so that's good. And it turns out that there's no linear term here, so we actually don't need this part at all. And you can eliminate that part just by making A equal to 0. Then A will zero out all of that. Okay, and now the thing that's the objective function for the generic QP problem has just become the SVM objective function. So we've succeeded in programming in the SVM objective into the QP context here. So the next thing to think about is how to enter the constraints. So here are the constraints. We have n of them, and so we can express this as a QP constraint in the following way. So A is going to have n rows. So what A is going to be is sort of just like X, except that every row here is not just going to be, so here's y1 times x1. Okay. So, you know, y1 is just plus or minus 1. So this is a scalar times a vector, so it's still a vector. And then here's y2 times x2 is the next row, and so on, all the way down. Okay, so we have one of those for every point in the training set. So now if we look at what happens when we do A times W, then you know, A times W is just going to be equal to a vector of, you're going to get y1 times the dot product of W and X, 1, and then y2, the dot product of W and X2. So that's exactly what we want, all the way down. Okay, and now we're ready to set up the rest of the inequality here. And to make it be the support vector machine system of inequalities, we just need ones in every place here. Okay, so V is just going to be a vector of n ones. And so you have to figure out how to do this in NumPy, but it's easy. Right. So now let's talk about the library that we're going to use. So we're going to use Quadprog. And so you can import it like this. I assume that it's on CoCalc, but I haven't verified that. Man, this would be a real disaster if Quadprog is not on let's just try it right here. No, this is a dumb waste of time. Sorry about that. So I assume that Quadprog is on CoCalc. If it's not, we can probably get it installed. So if you look at the actual function that is in the Quadprog library that solves the quadratic programming problem is called solveqp. And just like any Python function, you can get the documentation by putting a question mark after the function and then entering that cell. So that produces this. So here, this is just an awful ASCII version of what we were just describing. This X here is what we call W. I tried to make the notation match as much as possible. Capital G is what we called capital G. A is what we call A. For some reason, Quadprog prefers to think of the transpose here. I don't know why. It adds pointless complexity. But when you can construct this matrix up here, A, that we just discussed, when you put it into Quadprog, you're going to need to do A dot T because it wants the transpose of that. So that's a little wrinkle. And then what they call B here will be what we call V. And the reason I didn't want to reuse B is because we're using that for the bias weight. So something here I didn't notice until actually this morning, but it caused me some problems. It says that it's based on a numerically stable dual method for solving strictly convex quadratic programs. So I didn't know what strictly convex meant, I guess. And so let me explain that. So strictly convex means that that WTGW is strictly greater than 0. And the problem with that is that the G that I actually just told you to build, and which actually is the one that you should build, is not strictly greater than 0, it's just greater than or equal to 0. This is an important property of a matrix. If this is true, you say that it's a positive definite matrix. And if this is true, it's a positive semi-definite matrix. So you need it to be positive semi-definite for the problem to be convex. And so convex optimization problems have good properties. The one that we've talked about before is that the minimum is unique, so that's good. It has other advantages too, relating to the dual. You might notice there's a reference here to the dual, which we'll get to later, in case this wasn't complicated enough. So when you have a convex optimization function, the dual also has the same solutions as the original, which is an important fact for support vector machines, which we'll talk about later. Anyway, the long and short of this is that if you just type in G the way I described it above, this stupid thing will tell you that G is not positive definite. So how do you fix that? You just have to do this. So this is explaining what to do. So once you've cooked up G, just add a little sprinkling of positive but negligible numbers to the diagonal. So that's what this will do. It just adds like 1/1,billion to every element on the diagonal. So it doesn't affect the optimization too much, and it makes G positive definite instead of positive semi-definite. Okay. So this just explains the differences in notation, and a lot of these parameters here are optional. So MEQ is an optional parameter. We're going to ignore it. We're going to ignore it. You should be passing 4 things to quadprog: G, A, and then we call this capital A. You can call it C if you want, but that's going to collide with the traditional notation for the regularization parameter and SVMs that we're going to talk about in a second. And then we call B V. So you could give it just GA, capital A, V. Should be passing it 4 parameters. Okay. So here's where you can just do all that stuff that we just described. And when you do, you should get this W. And here's what it looks like. It's beautiful. It finds this maximum margin separator, and you can even see what the support vectors are. So there's 2 support vectors here, one there and one there. And here's what they are. So on the positive side, it's like 0.4 and 0.75. So here's like 0.4, 0.75. So it's this guy. And then on the negative side, it's minus 0.7, minus 0.7. So it's like, I guess it's that one. I don't know. So, with 2-dimensional data, and if it's kind of randomly distributed, you're going to have 2 support vectors, and you can kind of, that goes on to other dimensions. So in 13 dimensions, if you have kind of randomly distributed data, you're going to end up with 13 support vectors. And why do you care so much about support vectors? It turns out that, well, here, the support vectors are sort of the only thing that matter. You could throw away all the other data points, and if you just kept the support vectors, you would get exactly the same solution. So they kind of contain all the information here, all the relevant information in just 2 points. And also, in order to make predictions, the support vector machine just needs the support vectors to make predictions. So it compresses the information in the training set into just 2 points. And here's where we make the 3-dimensional version. I just mostly wanted to show you this picture to explain the equations for the margins. Okay, so let me stop for a second and take questions, because that was the warm-up, and now we're about to get serious. But I know that was already pretty complicated. Anybody have any questions? Okay. So now we're going to go on to, what's the capital of Nevada? Anybody listening?
I just don't know that, but I heard it.
Okay.
The capital, I don't know.
Yeah,
Yeah.
nobody knows the capital of Nevada. I was just checking that nobody knew it to make sure that everything was normal. Is it Carson City? Is that? I don't know. I think it's
It
Carson
is
City.
Carson City.
Okay, thank you. Thank you, Ray. All right. So now we're maybe instead of reading all this text to you, I'll just scroll down here and show you a picture. So it's that was cute and all that it works for linearly separable data, but if we've seen enough real data sets to sort of know that real data is not linearly separable. There are going to be exceptions. So that optimization process that we just went through doesn't work if the data is not linearly separable. So what do we do then? So the answer is these little squiggles. These are the Greek letters zeta. These are called slack variables. And so here's another thing that was a problem for me when I first studied support vector machines. There is one slack variable for every training point, and I guess my brain didn't want to accept that, or it didn't seem like it was right, but it's true. So there's one, every training point has its own slack variable. And what the slack variable records is like how much it's violating the margins. So if it's on the right side of the margin, the slack variable it has a value of 0. So that's no penalty. And then it penalizes points for being inside the margin, and it penalizes them sort of in proportion to how far they are on the wrong side of the margin. So if you got up to, if there was being exactly on the decision boundary would give you a slack variable value of 1. And then if you were over here, this would be 2. And then over here, this would be 3. So you have a budget of slack, but you want to use the smallest possible amount of slack. And so maybe I should look through this stuff and see if there's anything we need to say out loud. The hard margin approach, obviously, we've already said that a lot of data is not really linearly separable, but also the hard margin approach is sensitive to outliers. So if you put in one crazy data point, you can totally tilt the decision boundary, which is not good. Okay, so to relax the hard margin assumption, we have to allow margin violations. So margin violations are points that are inside the margin or even worse, completely on the wrong side of the decision boundary. This is a margin violation. So everywhere the slack variable is not 0, that's a margin violation. Okay. So we have to now sort of balance two different desires. We still want to have as wide a margin as possible, but as we make the margin wider, we're going to need more slack. So we also want to use the least amount of slack necessary. And so now it's going to be an optimization problem that's going to also involve these slack variables. So here's the old constraint. We just wanted this is just saying that every training point is on the right side of the margin. And this is saying that every training point is on the right side of the margin if you give it that much slack. So every training point, oh, there should be an N here. This is a typo. Let me try to fix that with my pen here. So there should be a little N right there. So for this training point, it should be on the right side of the margin, except it has a little bit of slack, and it has sort of just as much slack as it needs. And the slack variables always have to be non-negative. Okay. So this is what it amounts to mathematically. So this is kind of like augmented error. So this C here is a hyperparameter, and it's a weight that determines how much we hate margin violations. So if you really hate margin violations, then you want to crank up C and make it be a really big number, and then it will really punish having big slack variables, which will narrow the margin, but you'll have fewer margin violations. So this is a hyperparameter that just has to be tuned. You know, you guys have been, you're doing an assignment right now about tuning hyperparameters, so you kind of know how that works. So this is mathematically what we want to minimize. And all right, and notice that now there are more variables. Like this was definitely a problem for me when I was learning about this stuff. The minimization is with respect to a lot of variables. We want to minimize this expression with respect to d+1 variables just for w, and then n more variables for the slack variables. So it seems crazy, but we actually are going to find the minimum for this hugely multivariate problem. And now here are the constraints. So we need one of these inequalities for every training point, and then we need one of these inequalities for every slack variable. So now coding this as a quadratic programming problem is a little bit more challenging. But I think we talk about that later. So what does it say now? It's just explains what the effect of C is here. So if C is large, then margin violations are heavily penalized here, and that will make the margin be smaller. So this is a C of 1, and you can see the margin is kind of narrow here. But if you make C a tenth, then the margin gets wider, and you have many more margin violations. Okay. All right. So that'll be interesting when we also look at non-linear separators, because it'll be more clear how this relates to variance. So if you have a non-linear separation and if you don't tolerate margin violations, then that makes the line be very squiggly, which makes variance go up. So as C goes up, you get squigglier lines. Okay. All right. And so now let's try to explain the how we phrase all that as a quadratic programming problem. We still have the same basic setup for quadratic programming here. You know, that it sort of only does one thing. So now I'm using Z instead of W, and that's because we have so many more variables. So now the set of variables that we want to minimize are all of these variables. And I kind of left this to you. A lot of this is explained in the dynamic E chapter on support vector machines that you can get at www.amlbook.com. amlbook.com. Okay, but let's kind of walk through how this can work now. So let's just look at this problem first. So what kind of a thing can G be to make this true? And so you have to be kind of good at matrix multiplication to see how this is gonna work. So you've got ZT, G, Z. So here I'm going to draw sort of a sketch of how G can work. So first of all, G needs that 0 there, like it had before. G00 should be 0. And that lets us do the array slicing part here where we don't include the bias weight. Okay, so we need that. And so we need this little copy of the identity matrix here, which is, you know, this is D by D. Sorry, that doesn't look good. It's a pain to erase on this whiteboard. So this is the D by D identity matrix. Okay, and but we don't care about all of these slack variables at all here. So we just put in a big 0. And so what is this? This is like an n by n 0. And then everything off the diagonal is zeros. So you have to use NumPy to build a matrix like that. That's what G is going to be. And what that will give you is this, that ZTGZ is just that. Okay, so now we use the linear part. We didn't use the linear part at all before. The linear part now is going to give the, what are we supposed to be minimizing here? We're supposed to minimize W array slice. Man, maybe I can see why people choose not to do the array slicing. 1, okay. So we're trying to minimize that plus C times the sum of the slack variables. So this is I goes from 1 to n. So this is what we want to minimize for the SVM problem. So we've just talked about where this comes from. So that part comes from the matrix G. And now we want this part to come from the matrix A. The reason we have this negative sign here is because this is negative. So we need the negative of a negative to make this positive here. So we need to choose A so that A times Z is minus C times the sum of the slack variables. So how can you do that? So one thing, you know, if you are not strong in linear algebra, or you haven't had that much of it, just think about what happens if you were to dot product some this is a bad choice of variables. Let's introduce, what can I use as a vector name that we just aren't using at all? There's probably not one. I'm going to use M. This is pathetic. If you just do M dot product a bunch of ones, what happens here? This just becomes the sum of the M's. So that's almost what we want to happen, because we do want the sum of the slack variables. We also want this this hyperparameter C to be involved, but that's okay. We can just change these ones to C's. So you do M1 times, let's just go all the way and make it minus C. So make a bunch of minus C's here. And then this will be minus C times the sum of the M's here. So that's looking pretty good. The only problem is that we also have these W's at the beginning of Z. So let me erase all of this. Okay. All right. So how are we going to set this up as a dot product? Let's make a little. Let's just say that this is A, and over here let's write Z. So at first, in the top of Z here, there's a bunch of W's. There's W0, W1, down to WD. So for all of those, we just want zeros here because we want to zero them out. We don't care about them. So for every one of those, so there's going to be D plus 1 zeros to begin in A. And now for the rest, we have the slack variables. And for each of those, we want it to be multiplied by negative C. So we want a bunch of negative C's here, and then there are n of those. So that's how you build A. And what else is left to do? So that is it for the objective. We just explained how to express this entire objective. And now the question is, how do you deal with the constraints? Yeah. Okay. So here are we want to express two kinds of constraints. I'll be honest with you, it took me a while to figure this out. So doing this was easy. And then after I did that, I realized, oh, also the zetas have to be positive. So how can you do all of that? And to be honest with you, I don't really remember. But I think what you have to do is you have to rewrite this as YI WT x plus, and then you have to move the zeta over there, and this will be greater than or equal to 1. Is that right? Yeah, that must be true. So now what kind of a thing can A be to make that true? So one part of A, we still want this stuff, right? So we're gonna have like a sort of y times x here. So what do I mean by that? By that I mean it's gonna be a bunch of rows here. Here's like y1 times x1 all the way across, and then all the way down to yn times xn. So those are going to be the rows of this matrix. And now out here, that will get you this part, but now you want to pick out the corresponding slack variable from z. So the corresponding slack variable is going to be like over here in this part of z. You know, this whole thing is getting multiplied times z over here. So you know, you've got to pick out something in this region. So what we just did sort of takes care of this first part, and now we've got to deal with that stuff. So this is kind of like the identity matrix. So something like the identity matrix will work over here. So in the you know, when you're dealing with the first row of this, then this will be 1, and that will pick out the first slack variable. And then as you go through it, you'll just see that it makes sense. Okay, now what else? So that deals with this. Okay, and yeah. So now v, as before, this v vector is going to be mostly 1s. So it's going to be 1, 1, 1. How many of those 1s will there be? There's going to be n of those 1s at first. Okay. And now we have to think about this other constraint, the constraint about all the zetas being equal to, or being positive. So how can we do that? So that has nothing to do with the data part. That just has to do with the slack variables. So again, we'll just use the identity matrix to pick out these slack variables one at a time. And so now we're going to be comparing that to the lower part of V. And so these V's, after a certain point, V will just be zeros. And so there's going to be n of those zeros there. Okay, so I believe that's right? Yeah, okay. So that's a sketch of how to do it. I know that it's kind of hard. Some people, honestly, might not be able to, like if you didn't take the linear algebra prerequisite, don't worry, you're not going to fail the class, but I'm going to keep this as an assignment, just as a challenge to the people who are interested in it. And if you didn't like my presentation, there is for sure a better presentation in the book. Okay, so what else have we got here? So that's probably, oh, well, we could go through here and look at these pictures, I guess. So when you get all that working, you can look at the effect of varying C. So that's what these pictures do. Here C is getting bigger and bigger, and you can see that it's making the margins smaller and smaller. And eventually it's kind of hard to tell, but this, maybe you can see there, this is not exactly the same red line every time. And look, every time there's some support vectors on the margins. So what's happening between here is the support vectors are changing also. And it's really the support vectors that determine everything. Then when C gets really big, it gets very narrow margin. So that means high variance, and you might be overfitting depending on how many data points you have. So we'll stop there. You have these slides on CoCalc, so if you want to read ahead, you can. Sorry for the rustling. I'm looking for the attendance sheet. So you guys think of questions, and I'm going to just dig out the attendance sheet real fast. And we can stop the the sharing. Stop sharing. Okay, and stop.